At 9:12 a.m. on May 14, 1943, Lieutenant P.A. Bodinet walked across the tarmac at Reykjavik Air Station in Iceland toward his VP-84 Catalina, preparing for a patrol that would test a weapon nobody was supposed to know existed. Bodinet was 24 years old, 17 months in theatre, 29 anti-submarine patrols, 0 confirmed kills. German U-boats were hunting convoy HX-237 somewhere between Iceland and Greenland. Intelligence said at least 4 submarines were operating in the search zone. Bodinet would be flying straight into their patrol area with a weapon that officially did not exist. The PBY was slow, vulnerable, barely armed. Maximum speed 115 miles per hour. The Germans called them flying boats, easy targets. But the Catalina could stay in the air for 24 hours, could land on water, could cover vast stretches of ocean looking for submarines that spent most of their time invisible beneath the surface. The problem with hunting submarines wasn't finding them. Aircraft had radar now, could detect surfaced U-boats from miles away. The problem was killing them. Depth charges were the standard weapon. Drop them near where a submarine dived, hope one detonated close enough to rupture the pressure hull. But submarines were fast underwater, could change course after diving, could go deep where depth charges couldn't reach. The numbers were brutal. In April 1943, Allied aircraft dropped over 1,000 depth charges against U-boats in the North Atlantic. They sank 9 submarines. Less than 1% effectiveness. You needed perfect timing, perfect placement, perfect depth setting. Even then, most submarines escaped. Every patrol squadron briefing included loss numbers. Throughout the spring of 1943, U-boats were sinking merchant ships faster than the Allies could replace them. The convoy system helped, but submarines were still winning. They operated in wolf packs, coordinated attacks, hit convoys at night when aircraft couldn't see them. Even when aircraft caught submarines on the surface during daylight, the boats could crash dive in 30 seconds and vanish. That morning, Bodinet's aircraft carried something different. Strapped beneath the Catalina's fuselage was a device officially designated as the Mark 24 mine. The designation was a lie. It wasn't a mine. It was an acoustic homing torpedo. The Navy called it a mine for security reasons, to hide its true nature from German intelligence. The weapon had another name, used only in classified documents and whispered conversations. FIDO. The name meant dog determination, the torpedo that wouldn't quit. The weapon was so secret that pilots could only drop it under specific conditions. The submarine had to be submerged. The conning tower hatch had to be closed. No German could see the torpedo hit the water or watch what happened next. If any U-boat crewman witnessed FIDO in action and survived to report it, the secret would be lost. The restriction meant missed opportunities. Pilots found surfaced submarines, attacked with machine guns and depth charges, watched the boats dive, then couldn't drop FIDO because someone might have seen. 3 pilots in Bodinet's squadron had found submarines in the past month. All 3 attacked conventionally. None got kills. But today was different. Intelligence reported U-boats operating submerged near convoy HX-237, hunting with hydrophones, trying to get into attack position without surfacing. If Bodinet found one underwater, he could drop FIDO without restriction. Nobody would see. The weapon could prove itself or fail in secret. The weapon looked deceptively simple. 7 feet long, 19 inches in diameter, 680 pounds, smaller than a conventional torpedo. Fat and stubby compared to the sleek weapons that torpedo bombers carried. The nose was hemispherical, rounded. The tail had 4 small fins and a single propeller. No external marks, no identification numbers, nothing to indicate what it was, just dull grey paint and a plain metal surface that concealed revolutionary technology inside. At 09:25, Bodinet climbed into the Catalina's cockpit. His crew of 9 men followed. They would be airborne for 18 hours, patrolling a rectangular search zone, 400 miles long and 200 miles wide. If they found a submarine, they would attack. If they found a convoy under attack, they would defend it. If they found nothing, they would return to Reykjavik exhausted and try again tomorrow. The Catalina taxied to the end of the runway, took off, climbed into the grey morning sky and turned southwest toward Greenland. 18 months earlier, the weapon Bodinet carried hadn't existed. The path from concept to combat began in a meeting room at Harvard University on December 10, 1941, 3 days after Pearl Harbor. The United States wasn't officially at war yet, but scientists and military officers already knew submarines would be the critical threat in the Atlantic. British convoys were being savaged by German wolf packs. Existing weapons weren't working. Something new was needed urgently. Admiral Louis McKeon from the Bureau of Ordnance called the meeting. McKeon was a physicist before the war, former director of Yale University's physics laboratories. He understood acoustic theory, understood underwater sound propagation, understood what might be possible if someone could build a torpedo that listened for its target instead of running blind. He invited 2 groups to the December meeting: Harvard Underwater Sound Laboratory, led by Dr. Frederick Hunt, and Bell Telephone Laboratories, represented by their acoustic research division. McKeon's challenge was simple: design an air-dropped acoustic homing torpedo, make it small enough to fit on patrol aircraft, make it powerful enough to kill submarines, make it smart enough to find targets underwater, make it reliable enough to work in combat conditions, and do it in less than a year because men were dying every day in the North Atlantic. The meeting lasted 4 hours. By the end, both Harvard and Bell Labs had agreed to pursue independent parallel development programs with complete information sharing. It was an unusual arrangement. Normally, competing contractors worked in isolation, but the urgency was too great for normal procedures. Everyone in that room understood that submarine losses would determine whether Britain survived or starved. The project got official designation on December 22, 1941. Office of Scientific Research and Development, Project 61. Code name FIDO. The name was deliberately ambiguous. Some thought it meant faithful, like a dog tracking its target. Others said it meant dogged determination. The real reason was more practical. FIDO was easy to remember, hard to confuse with other projects, and gave no clue about what the project actually did. The technical challenges were enormous. Acoustic homing required detecting submarine propeller noise underwater, distinguishing it from ocean background noise, calculating the direction to the target, and steering the torpedo toward it. All of this had to happen automatically without human control, because once the torpedo was in the water, no one could adjust it or guide it. The weapon had to be completely autonomous. Underwater acoustics in 1941 was a primitive science. Researchers knew sound traveled through water but didn't fully understand how depth, temperature, salinity, and pressure affected propagation. They knew propellers made noise but couldn't precisely characterize the acoustic signature. They knew listening devices existed but weren't sure if they were sensitive enough to detect submarines at useful ranges. Everything was theoretical. Nothing had been proven. Dr. Eric Walker was Associate Director of the Harvard Underwater Sound Laboratory, a specialist in acoustic propagation. Walker had earned his doctorate from Harvard in electrical engineering and had been working on underwater acoustics since the late 1930s. When the FIDO project began, he became responsible for coordinating the testing program that would determine whether acoustic homing was practical or just a theoretical dream. The Harvard team focused on magnetostrictive hydrophones. These used changing magnetic fields to detect sound pressure changes in water. They were sensitive but required careful calibration and generated their own electrical noise that could mask weak target signals. The Harvard approach used 4 hydrophones arranged symmetrically around the torpedo body, each listening to a different direction. Compare the signal strength from each hydrophone, determine which one heard the loudest propeller noise, and steer toward that direction. The Bell Labs team used piezoelectric hydrophones. These generated electrical voltage directly from pressure changes, with less internal noise than magnetostrictive designs. Bell's system also used 4 hydrophones, but processed the signals differently. Instead of simple bang-bang steering, where the rudder went hard left or hard right, Bell developed proportional steering, where rudder angle was proportional to the signal strength difference. The theory was that proportional steering would be smoother, more accurate, less likely to overshoot the target. Both teams worked frantically through December and January. Western Electric developed the battery, a 48-volt lead-acid system that had to provide 110 amps for 15 minutes while surviving the shock of airdrop and water entry. General Electric designed the electric motor, a 5-horsepower unit that could drive the torpedo at 12 knots underwater. David Taylor Model Basin created the hull design by modifying an existing Mark 13 torpedo airframe, shortening it and widening it to create the stubby shape that could accommodate the acoustic equipment. By February 1942, components were coming together. By March, the first prototypes existed. By April, both Harvard and Bell Labs had working torpedoes ready for testing. The testing happened at Key West, Florida. Remote location, warm water, minimal ship traffic, maximum security. Navy provided a submarine as target. The submarine would run submerged at various depths and speeds, while engineers dropped prototype torpedoes and tracked their performance. Walker spent April and May of 1942 at Key West, personally supervising every test run. The early failures were frustrating but expected. Nobody had ever built an acoustic homing torpedo before. In the first tests, the torpedoes either failed to detect the target submarine entirely or detected it but steered erratically, sometimes toward the target, sometimes away, sometimes in circles. The problem was distinguishing the target signal from background noise. Ocean water is never quiet. Waves create noise. Marine life creates noise. The torpedo's own motor and propeller created noise. The hydrophones picked up all of it. Walker's team had to develop signal processing techniques that could filter out everything except the distinctive sound of submarine propellers. By June, the torpedoes were reliably detecting targets at ranges up to 1,500 yards. By July, they were tracking targets through simple maneuvers. The Harvard system and Bell system both worked, but differently. Harvard's bang-bang steering was simpler, requiring less electronic complexity, but sometimes overshot targets during sharp turns. Bell's proportional steering was more complex, requiring more sophisticated vacuum tube circuits, but tracked smoothly through complicated maneuvers. The Navy had to choose one system for production. After reviewing test data from dozens of runs, they chose Bell's proportional homing design, but incorporated several Harvard innovations in the acoustic processing. The final production FIDO was a hybrid, the best features of both programs combined into a single weapon. Western Electric would manufacture them at their facility in Kearney, New Jersey. Production would begin immediately, even though airdrop testing was still incomplete. The decision to rush into production was calculated risk. The weapon wasn't fully tested. Nobody knew if it would survive the shock of airdrop from 200 feet. Nobody knew if it would work reliably in North Atlantic conditions with rough seas and high-noise environments, but the submarine threat was urgent. Every week delayed was another convoy attacked, another 100 merchant seamen dead. The Navy decided to accept the risk and hope the weapon worked. The first production FIDO torpedoes rolled off the assembly line in January 1943. Initial order was for 10,000 units at $1,800 each. Each torpedo was hand-assembled, hand-tested, hand-calibrated. Quality control was obsessive. Every component was inspected multiple times. Every torpedo was tank-tested before delivery. Reject rate was less than 2%. The weapons arrived at operational squadrons in March. Pilots received minimal briefing. This is the Mark 24 mine. Drop it when ordered. Don't ask questions. The less they knew, the better security would hold. Mechanics who loaded them got slightly more information, but only about handling procedures. The technical details remained classified. The manufacturing process at Western Electric involved hundreds of workers who had no idea what they were building. Components were fabricated in separate facilities. The battery came from Electric Storage Battery Company in Philadelphia. The motor came from General Electric in Schenectady. The propeller came from a small machine shop in Connecticut that normally made boat parts. The hydrophones were assembled in a secured room at Bell Labs in Murray Hill that required special clearance to enter. Workers assembled components according to specifications without understanding how the parts fit into the whole system. Quality control was extraordinary. Each torpedo underwent 23 separate inspection procedures before acceptance. The hydrophones were tested individually in acoustic chambers to verify sensitivity and frequency response. Engineers used calibrated underwater speakers to generate test signals at different frequencies and intensities, measuring how each hydrophone responded. The battery was discharged and recharged 3 times to verify capacity and ensure no cells had internal defects. The motor was run under load for 30 minutes to check for bearing problems or electrical issues. The entire assembly was placed in a pressure tank and subjected to conditions equivalent to 300 feet depth, to verify the seals would hold. Even with obsessive quality control, early production units had problems. The first batch of 50 torpedoes delivered in March had battery issues. The lead acid cells developed internal shorts during shipping because the mounting brackets allowed too much vibration. Western Electric redesigned the battery mounting system with additional shock absorption and rubber isolation. The second batch had propeller problems. The blades were slightly out of balance, causing vibration that disrupted the acoustic sensors. The propeller manufacturer implemented tighter machining tolerances and began dynamically balancing each propeller before installation. The third batch had depth control problems. The bellows mechanism that regulated search depth was too sensitive to water temperature changes. Engineers modified it with a temperature-compensating spring that adjusted for thermal expansion. By May, production units were reliable. Squadrons received their first FIDO shipments in late April. By early May, only 12 operational aircraft carried the weapon. The rest were still equipped with conventional depth charges while maintenance crews trained on loading procedures and security protocols. On May 12, 1943, an RAF Coastal Command Liberator from Squadron 86 found U-456 on the surface west of Ireland. The submarine crash dived. The Liberator dropped a FIDO as the conning tower disappeared beneath the waves. The torpedo detonated underwater approximately 4 minutes later. The crew observed oil and debris rising to the surface. They circled the area for 30 minutes but saw no submarine resurface. Later that same day, HMS Opportune detected U-456 trying to dive again and finished it with depth charges. 49 men died. The submarine never radioed for help, never fired distress flares. It simply vanished. The Admiralty credited the sinking to depth charges in their public report, but the classified assessment reached different conclusions. FIDO had critically damaged the submarine, rupturing pressure hull sections and flooding compartments, making it vulnerable to the final attack. The acoustic homing system worked. 2 days later, on May 14th, Bodinet would prove it worked again. At 13:18, Bodinet's radioman picked up a radar contact 15 miles northeast. Surface contact, moving southwest at approximately 10 knots. Bodinet turned toward the contact and descended to attack altitude. At 8 miles, the radar operator confirmed the target was a submarine. At 4 miles, the surfaced U-boat spotted the Catalina and began its crash dive. Bodinet saw the bow go under, saw water washing over the deck, saw crewmen scrambling through the conning tower hatch. He was too far away to attack with machine guns. The submarine would be completely submerged before he arrived. This was the scenario the orders described. Submarine submerged, hatch closed, no witnesses. Bodinet armed FIDO and set up his attack run. He overflew the dive point at 200 feet altitude, traveling 110 miles per hour. At the exact moment his bombardier calculated the submarine's probable position, Bodinet released the torpedo. FIDO fell away from the aircraft, nose first. It hit the water 73 yards from where the submarine had vanished. Bodinet's crew watched the splash, saw the weapon disappear beneath the surface, then saw nothing. No wake, no visible propeller trail, nothing to indicate where the torpedo went. The electric motor left no bubbles, no disturbance. The weapon was invisible. For 4 minutes, Bodinet circled the area at low altitude. His crew saw nothing unusual. No debris, no oil slick, no indication of what was happening underwater. But beneath the surface, FIDO was hunting. The torpedo descended to 150 feet and began its programmed circular search pattern. The 4 hydrophones listened in all directions, filtering the ocean noise, searching for the distinctive sound of submarine propellers. Then, at 13:23, approximately 4 minutes and 30 seconds after FIDO entered the water, the ocean surface erupted. A massive underwater explosion created a dome of white water that rose 50 feet into the air. Oil and debris followed immediately. Pieces of metal, fragments of deck plating, sections of wooden gratings. An oil slick began spreading across the surface, dark and thick. Bodinet's radioman immediately transmitted the attack report. Submarine contact, attacked with special weapon, observed explosion and debris, probable kill. He didn't mention FIDO by name over open radio. Security protocols forbade it. The message went to Reykjavik, encrypted, decoded by intelligence officers who knew what special weapon meant. Bodinet landed at Reykjavik at 02:14 on May 15th after 18 hours and 32 minutes airborne. He climbed out of the Catalina exhausted, his flight suit soaked with sweat. Intelligence officers were waiting to debrief him. What he had accomplished would remain classified for decades. The submarine Bodinet Sank was U-640, commissioned in September 1942, operational since January 1943. It was on its first combat patrol, hunting convoy HX-237. The commander was Oberleutnant zur See Karl-Heinz Nagel. His crew of 49 men averaged 23 years old. 12 were on their first patrol. German records indicate U-640 dived at 13:14 to evade an aircraft contact. The boat leveled off at 150 feet and began a standard evasion pattern. Based on submarine operating procedures and hydrophone capabilities of the era, the crew would have detected the torpedoes' approach through their listening equipment. They would have heard a high-pitched sound, growing louder, closing from astern. The commander would have ordered evasive maneuvers, depth changes, rapid turns, everything in the evasion manual. But FIDO tracked the submarine through every maneuver. The acoustic homing system adjusted continuously, steering toward the loudest propeller noise. At 13:23, the torpedo closed to contact range and detonated. The explosion ruptured the pressure hull. The submarine flooded instantly. Emergency procedures were useless. The boat lost all power, all control. It sank through increasing depths until the pressure hull collapsed. Everyone died within seconds. 2 hours later, when U-640 failed to report its position, German headquarters in Lorient assumed it had been lost. They didn't know how. They didn't know what weapon had killed it. They just knew another boat was gone. The Germans first noticed something wrong in late May. Submarine loss rates in the North Atlantic suddenly increased. Not dramatically at first. Just a steady uptick in boats that failed to return, boats that radioed contact reports and then went silent, boats that vanished without trace or explanation. The staff intelligence officer at U-boat headquarters in Lorient analyzed loss patterns. In early June, he compiled a report on May submarine operations. 41 U-boats lost, the highest monthly loss rate of the entire war. Most were sunk by aircraft or surface escorts in circumstances that looked routine. But something was different. U-boats radioed that they were diving to evade aircraft. Then silence. No further transmissions, no distress calls, no surfacing reports, just boats that dove and never came back. In previous months, submarines attacked by aircraft usually survived the first attack. They would report damage, request support, attempt to reach port. But in May, boats were dying on the first attack. Something had changed. The survivors reported strange phenomena. Several commanders described distinctive high-frequency sounds that followed their boats through evasion maneuvers. One boat reported hearing such sounds for over 3 minutes before losing contact. That boat survived because the sound suddenly stopped and moved away, suggesting the pursuing weapon had either malfunctioned or exhausted its power. German intelligence suggested the Allies had developed a new acoustic weapon, probably torpedo-based, probably dropped from aircraft, definitely capable of homing on submarine propeller noise. The report went to Admiral Karl Dönitz, commander of the U-boat fleet. Dönitz initially dismissed it. Acoustic torpedoes were theoretically possible but technically difficult. The Germans themselves had been developing acoustic torpedoes since 1933 and still hadn't perfected them for anti-submarine use. But the loss patterns were undeniable. In June, German Submarine Command issued new tactical orders. When diving to evade aircraft, shut down all machinery except essential systems, minimize propeller noise, change depth and course immediately after diving. Don't maintain steady depth or speed. Make yourself as quiet as possible and move unpredictably. The countermeasures didn't work. June losses were 32 boats, July losses were 37. The mysterious weapon kept killing submarines. German intelligence officers interrogated Allied prisoners and searched wreckage from downed Allied aircraft looking for clues. They found nothing. The security around FIDO was absolute. By August, German submarine crews faced a psychological crisis. They knew that diving near Allied aircraft meant probable death from an invisible enemy. Some commanders refused to dive when aircraft appeared, instead choosing to fight on the surface with anti-aircraft guns. This made them more vulnerable to conventional attacks, but at least gave them a chance to shoot back. Diving meant dying blind, pursued by something they couldn't see, couldn't outrun, couldn't escape. The psychological impact was devastating. German submarine crews went from hunters to prey. They lost the initiative. Patrol patterns became defensive. Boats that spotted convoys often refused to attack because it would require submerging near aircraft. The wolfpack tactic collapsed because boats couldn't coordinate attacks without surfacing to communicate, and surfacing meant aircraft might force them to dive into range of the invisible weapon. In September, Dönitz ordered all Type 7C submarines, operating in the North Atlantic, to install additional sound-dampening equipment on their propellers and machinery. The modifications took 3 weeks per boat and reduced their underwater top speed from 7.6 knots to 6.3 knots. The theory was that quieter submarines might evade the acoustic weapon. The practice showed otherwise. FIDO killed the modified boats as efficiently as the unmodified ones. The torpedoes' hydrophones were sensitive enough to detect even the quietest submarines at operationally useful ranges. The Germans never solved the problem. They developed their own acoustic torpedoes, the G7E Zaunkönig, specifically designed to hunt escorts by following their propeller sounds. But the G7E was designed for attacking surface ships from submerged submarines. It ran at a preset depth and couldn't pursue targets through three-dimensional maneuvering. The German torpedo was effective against surface vessels, but couldn't counter FIDO's capabilities. The final German analysis of submarine losses came in March 1944. Intelligence officers determined that Allied aircraft were using some form of acoustic weapon that activated after water entry, searched for targets using passive listening, and guided itself to impact. They estimated the weapon had a range of approximately 4,000 yards and a runtime of 10 to 15 minutes. They were remarkably accurate in their assessment, but by March 1944, it was too late. The Battle of the Atlantic was over. Allied aircraft and escorts had broken the U-boat fleet. The training Bodinet received for FIDO operations lasted 4 hours. An intelligence officer from Washington flew to Reykjavik in late April with classified briefing materials. He gathered 12 pilots in a secured room and explained the operational procedures. The Mark 24 mine is an acoustic device. It detects propeller sounds underwater. Drop it in a circular pattern around the submarine's last known position. The weapon will search automatically. Do not drop it if the submarine is on the surface. Do not drop it if anyone on the submarine might observe the attack. Maintain absolute secrecy. That was the entire briefing. Bodinet asked questions about effective range and search time. The intelligence officer said that information was classified. Everything about the weapon's performance was classified. Just follow the drop procedures and file reports using the code word special weapon. Never write Mark 24 mine in any unencrypted communication. Never discuss it outside secured spaces. The drop procedures were precise. FIDO required specific altitude and airspeed. Too high and the impact shock would damage the battery. Too fast and the weapon might tumble on water entry and fail to stabilize. The optimal drop parameters were 200 feet altitude, 110 miles per hour airspeed, level flight. Aircraft had to overfly the target point exactly, release at the calculated moment, then turn away immediately to avoid being overhead if the torpedo detonated near the surface. Pilots practiced the drop procedures without live weapons. They used dummy training units filled with sand to match the weight and aerodynamic properties of operational FIDO torpedoes. The dummy units had no electronics or propulsion systems. Pilots dropped them in designated practice zones offshore, circled to observe the splash, and evaluated their accuracy. The training emphasized precision. A miss by 50 yards might mean the difference between a kill and a failed attack. Over the next 2 years, FIDO sank 37 submarines, 26 German boats in the Atlantic, 11 Japanese submarines in the Pacific. Every kill followed the same pattern. Aircraft found submarine on surface. Submarine crash dived. Aircraft dropped FIDO near the dive point. 4 to 7 minutes later, underwater explosion and debris field. No survivors, no wreckage substantial enough to reveal what had killed them. The effectiveness was remarkable. Conventional depth charges had a 9.5% kill probability against submerged submarines. FIDO had an 18% kill probability, nearly twice as effective. But the real advantage wasn't the kill ratio, it was the psychological impact. German submarine crews knew something was killing them underwater but didn't know what or how to defend against it. That uncertainty was more effective than the actual weapon. It paralyzed German tactical thinking and forced them into defensive postures that negated their advantages. In August 1943, a marine dive team recovered fragments of a FIDO that had washed ashore on Newfoundland after a storm. The torpedo had failed to arm properly during a training exercise and ended up on a beach. Security procedures required immediate demolition. A team from Naval Intelligence arrived within 6 hours. They photographed the fragments for technical analysis, collected every piece larger than a fist, loaded everything onto a truck, drove it to a remote location, and burned it with thermite incendiary devices. They sifted through the ashes afterward to ensure nothing survived that could reveal the weapon's design. The security was absolute. Nobody outside the program knew FIDO existed until after the war. German intelligence never discovered the secret. Japanese intelligence never suspected acoustic torpedoes were being used against them. Even most Allied personnel didn't know. Pilots who dropped FIDO knew it only as the Mark 24 mine. Mechanics who loaded it had no idea how it worked. Intelligence officers who tracked kills compiled reports that attributed sinkings to depth charges or other conventional weapons. The compartmentalization was so complete that even senior naval officers in unrelated commands had no knowledge of the weapon. The weapon appeared in official documents for the first time in July 1946, when the Navy declassified selected wartime projects. The Mark 24 mine was described briefly in a technical summary of anti-submarine weapons. Total production, 4,000 units. Combat deployments, 340 missions. Torpedoes launched 204. Submarines sunk 37. Submarines damaged 18. Effectiveness rate approximately 18%, compared to 9.5% for depth charges. The report didn't mention the individuals who developed it. Dr. Frederick Hunt at Harvard, Dr. Eric Walker, who supervised testing. The engineers at Bell Labs, who designed the proportional homing system. Admiral Louis McKeon, who initiated the project. None received public recognition. The Navy attributed the weapon's success to institutional development processes, not individual genius. Eric Walker left Harvard in 1945 and founded the Ordnance Research Laboratory at Pennsylvania State University, which became the Applied Research Laboratory. The Navy asked Walker to bring approximately 100 engineers, scientists, and technicians with him to continue acoustic torpedo development. The lab continued this work for the next 50 years. Walker led development of the Mark 37, Mark 46, Mark 48, and numerous other advanced torpedoes. He received recognition for his post-war work, but never for FIDO, which remained classified during his lifetime. Walker died in 1995 at age 88. His obituary mentioned his contributions to naval technology, but didn't specify which weapons he developed. Frederick Hunt stayed at Harvard until 1948, then moved to the Massachusetts Institute of Technology. He became director of MIT's Acoustics Laboratory and trained the next generation of underwater acoustic specialists. He published extensively on sound theory, but never wrote about FIDO. The details remained classified. Hunt died in 1972. His legacy is in the acoustics textbooks that bear his name and the students he mentored, not in the weapon that helped win the Battle of the Atlantic. Admiral Louis McKeon returned to civilian life after the war and rejoined Yale University. He taught physics until retirement in 1963. Former colleagues remembered him as brilliant but modest. He rarely discussed his wartime work and never claimed credit for initiating the acoustic torpedo project. The official Bureau of Ordnance History mentions his role in one brief paragraph. His contribution to one of the war's most successful weapons programs remained largely unknown outside classified circles. The weapon itself stayed in service until 1948, when the Navy replaced it with more advanced models. The 4,000 production FIDO torpedoes were gradually retired, used for training exercises, or destroyed. A few ended up in museums, stripped of their guidance systems and electronics. Most were scrapped. By 1950, almost no physical evidence remained of the weapon that had terrorized German submarine crews and helped win the Battle of the Atlantic. In 1991, the Navy declassified additional FIDO technical documents. Historians could finally piece together the complete story. The December 1941 meeting at Harvard, the parallel development programs, the Key West testing, the rushed production decision, the combat deployments, the 37 submarines sunk, the absolute security that kept the weapon secret for years after the war ended. Researchers estimated that FIDO operations saved between 80 and 120 Allied merchant ships from submarine attack. Each ship represented 30 to 40 crew members, plus passengers on troop ships, plus cargo worth hundreds of thousands of dollars. The weapon's direct impact was measurable in submarines killed. Its indirect impact was in German tactical changes forced by fear of an invisible enemy they couldn't counter. The weapon that changed submarine warfare was conceived at a meeting in December 1941, developed in 8 months, put into production before testing was complete, deployed in absolute secrecy, used by pilots who signed oaths never to discuss it, killed 37 enemy submarines without any of them knowing what hit them, remained classified for decades, and gave credit to institutions instead of the individuals who built it. That's how innovation actually works in war. Not through official channels or standard procedures, but through urgent need, meeting brilliant people willing to work 80-hour weeks to solve impossible problems. Through commanders who took risks to approve untested weapons because the alternative was watching more ships sink. Through pilots who used those weapons without understanding how they worked because somebody told them it would save lives. Through scientists who developed them without recognition because classification prevented their work from being acknowledged. The 37 submarines sunk by FIDO represented over 2,000 German and Japanese submariners who died without knowing what killed them. Their families received notification that their loved ones were missing, presumed lost at sea. The families never learned the details. The submarines simply vanished. For decades afterward, naval historians tried to determine what happened to boats like U-640. The official records showed they were lost to aircraft attack. But the exact weapon remained mysterious until the FIDO documents were declassified. FIDO proved that acoustic homing worked. The technology developed for that first crude torpedo became the foundation for every acoustic homing torpedo built afterward. The Mark 27, cutie for submarine versus surface ship attacks, the Mark 37 for destroyers, the Mark 46 for helicopters, the Mark 48 for submarines, all descended from the design principles established at Harvard and Bell Labs in 1942. The hydrophone arrays, the proportional steering, the circular search pattern, the passive acoustic detection. Every modern anti-submarine torpedo uses variations of the same concepts that Eric Walker and his team developed at Key West in the spring of 1942. The men who built it never received proper credit during their lifetimes. The pilots who used it flew into history anonymously. The submarines it killed vanished without trace, and the weapon itself was called a mine to hide its true nature, even after the war when hiding the truth no longer protected operational security. If you found this story as compelling as we did, please take a moment to like this video. It helps us share more forgotten stories from the Second World War. Subscribe to stay connected with these untold histories. Each one matters. Each one deserves to be remembered. Leave a comment below telling us where you're watching from. Our community spans from Texas to Tasmania, from veterans to history enthusiasts. You're part of something special here. Thank you for watching, and thank you for keeping these stories alive.